Swayam Prabha. Digital India. Educated India.
Good morning. Once again I welcome you to this soil mechanics courses, and we have completed a few topics, and now we are going to start a very important topic, that is effective stress concept. And because this is actually now will be applicable in everywhere, whatever when you go for strength, when you go for compressibility, when you go for earth pressure, everywhere that effective stress is a very important topic or important term to be used throughout the soil mechanics course. So, one has to understand this effective stress calculation, because there are many applications. This initial part will be the calculation of effective stress, and so we have to learn the concept, how to find out effective stress, because the effective stress can be can vary place to place, time to time, because of the variation of soil, variation of water table, variation of flow condition. So, we will show one by one those things. So, first this is effective stress concept, actually whatever given in Tarjagi, given by Tarjagi in 1923, and this effective stress concept applies only to saturated soil and relates three important components, and they are actually: one is total normal stress on a plane within the soil mass, being the force per unit area transmitted in normal direction across the plane, imagining the soil to be a solid material. So, like if a block there, and if I apply a force P, that then if it is a solid one, then we generally can find out what is the stress at any point, that we generally do by P by A. So, that is the one normal stress, that is the first one. Total normal stress, generally we will tell that we will use the term total normal stress now onwards. So, that is nothing but P by area. If the cross sectional area of the soil through which force is applied, then the total stress is normal stress is P by A. And then second one is the pore water pressure. The pore water pressure being the pressure of water filling the all void spaces between the solid particles. So, I will show the next slide how the soil particles are together and make the soil mass, and what are the voids between the particles, and then this when saturated condition, then those void spaces will be filled up with water, and that water definitely based on the water table location, we can find out what is the pressure in the pore pressure, the hydrostatic pressure acting through in the soil grain. That is one. Generally we use this as a sigma. If I take this as a sigma and this we use as u, and the effective normal stress, this is a concept actually on the plane representing the stress transmitted through the soil skeleton only. That means, we will see that soil skeleton there will be a number of contacts, and this force will be transmitted through the contact only. So, that is what the effective normal stress on the plane, the same plane where we have imagined, but the stress transmitted through the soil skeleton only. So, I will show to the next slide the mechanism. So, generally we used sometime this is effective stress either by sigma dash, and sometime it is sigma bar. So, these are the things terminology, that is sigma is the total stress, not total normal stress, that is which is P by A, or if it is a self weight of soil, how to find out sigma, that we will discuss subsequently. And pore pressure is actually U, that means within the soil grains there is a void spaces, that void spaces when saturated will filled up with water, and pressure will depend on at what depth actually it is there. If the water table, it depends on the height of the water table, and the effective normal stress is another thing actually relates this sigma and nu. How it is relating, that we will see in the subsequent slides. So, this is actually if I see in the soil mass and in a very large view, if you think of, then we will see these are actually these are all soil grain. These are soil grains, and they have a number of contacts between the soil grain, and remaining portion between the contacts and of particles, this portion is voids. These are voids, and these voids will be saturated condition, will be filled up with water, otherwise it will filled up with air. Now, we can imagine a plane actually x x and through the contact points, and see the grains are very small. The inlet view looks like wavy, but it is generally from a in a actual grain, if you draw, it looks like a horizontal line, and when you draw this line, you will pass through a number of contact points, like this is one contact point, this is another contact, this is another contact point, this is another contact, like that. So, this whatever force you are applying, this force is some giving here, and these particles will be giving something here, something here, something here, and when this will transfer here, this will also give equal and opposite reaction. So, like that at this the plane, we can imagine the number of contacts, and each contact point there are number of forces acting, and those forces actually we can now divide or into take two components. One is in the perfectly vertical direction, see like that one I have shown here, this is normal and there is a tangential. So, two direction. So, like that if there are n number of contacts, so n number of normal force will be there, and they are random in direction, the direction is not known depending upon this the orientation of or position of the particles. So, their directions are generally not known, and but we can take now two components, one is vertical or horizontal, then the components in horizontal direction we can sum it to get the horizontal pressure or force, and we can add the vertical component to all components, then we will get the net vertical force. So, like that we can get. So, after getting this, so we can see how this can be used for developing the effective stress concept. Now, the interparticle forces are very random in both magnitude and direction throughout the soil mass, but at every point of contact on the wavy plane may be split into components normal and tangential to the direction of the true plane to which x x approximates. The normal and tangential components are n and t. Suppose n dash is the normal force at a contact points, and if I take a component, then suppose that is n and t, and finally, we can take that as per definition, that effective normal stress is the interpreted as the sum of all the components n within the area A. So, within the cross section of whatever number of contacts are there, that contact point whatever normal force is there, their vertical component will be taken and then summed it up like this sigma n dash we can do and divided by this cross sectional area. So, that is the actual by definition is the effective stress. So, this is the definition of it, that means through soil skeleton whatever force transmitted, that divided by the actual cross sectional area is the effective stress. So, this is the by definition, and total normal stress as we have defined, that sigma will be force P applied over cross sectional area A. So, that is actually by definition total stress sigma. And now, if I consider that plane x x where we have calculated considered that place, if we consider vertical equilibrium, that means all vertical summation of vertical forces will be equal to 0 or applied force will be equal to the resisting force. So, like that I can use, then I will get this equation. So, this is the force P applied externally, and that is like we have applied here and P, and we have taken the section here, and through interparticle forces, suppose sigma n is there, and then those void spaces there is a suppose pressure, water pressure acting is u. Suppose there is a two voids or something, voids are like that. In this there is a pressure that is suppose u. Then u, I have taken a cross sectional area. So, over the entire cross sectional area u is acting, suppose, because u is changing with the head, water head. So, since we are at a particular head, we are considering u is constant over the entire length, and then entire area. So, u multiplied by area will also give you this is actually u is the pressure, that is pore water pressure. Pressure multiplied by the cross section will give you force, and sigma n also is the force, the normal vertical direction, u also force in the vertical direction. So, this can be taken. So, u actually when there is u, when there is a grains like this, when there is a u acting, u will be acting equally all direction. So, I am considering only vertical direction. So, u into A is force, sigma n dash also force, these two together will be equated by the external force P. Now, if I divide by A to all, then you can see P by A, sigma n dash by A plus u. Now, this we have defined in the previous slide, that it is nothing but is sigma P by A, and sigma n dash by A is nothing but sigma dash, that is effective stress, and u is nothing but pore water pressure u. So, this can be finally our interest to find out the effective stress. Then your effective stress will become sigma dash will be equal to sigma total stress minus u, that is pore water pressure. So, total stress if you can calculate, and then if you subtract pore water pressure at a depth, then you will get the effective stress at that point. So, this is the concept of effective stress. This is the formula or relationship between u, sigma dash and sigma, and this will be applicable throughout the soil mechanics, and you have to learn very carefully this one. Until unless if you calculate properly, then other things will be also will not be able to do correctly. And now, these 2-3 points to be remembered, that effective stress is a concept actually, and here a number of things we have assumed. The pore water pressure is there within which acts equally in every direction, will act on the entire surface of the particles. So, there is a particles, there are number of particles, and very large number of particles, and compared to the number of particles and volume, the contact is very less. So, if total contact area is very less, and so because of that, that u is assuming to be applied to surface of any particles full, but is assumed not to change the volume of the particles. So, when there is a pressure acting to a particles from all direction, we are assuming that it is not causing any volume change. When they apply pressure, that is supposed to be volume change, but in a static condition they are in equilibrium, but they are not causing any volume change. So, that is the assumption. If you do not do this assumption, this cannot be developed. Also, the pore water pressure does not cause particles to be pressed together. So, there is, because of this pressure, they are not forcing two particles to come closer or going away in the static condition. That is another assumption. Now, the error involved in assuming point contact between particles is negligible in soil, mainly because the total contact area normally being 1 to 3% only, whatever the total area, and if you find out the summation of the contact points and if you take area, it comes only 1 to 3%. And so, whatever assumption we have made based on this point contact, so it will not give much error. Similarly, effective stress is a concept that what is the meaning of it? That is summation of normal load through the contact points divided by the total area. So, that is the effective stress. So, summation of the normal component through the contact point divided by area is the effective stress. Hence, it does not represent the true contact stress. That means, when there are two particles are in contact and between the contact, what is the stress? That is not really this one. This is actually is a concept we are getting that divided by area. So, because of that, whatever effective stress is getting, that intensity or magnitude is much smaller than the actual contact stress, and actual contact stress what it will be? It will be N by A, which will be much higher than the effective stress whatever we have defined. What is N? N is the total load, and what is the small a? Small a is the actual contact area, and which is actually only 3 to 4%. So, you can imagine that actual contact stress will be much higher than whatever we have defined by effective stress, and though we have defined the effective stress as the force transmitted through the soil skeleton, but that is there only for consideration of force, but when you are considering area we are taking entire area. So, that is a concept, as a concept has to be used, and that is being used. So, that is the thing to be remembered. Now, as I have mentioned that if you apply force, how stress will be distributed, that will come later on. We will discuss that when you force applied on a ground surface, how stress is developed within the soil mass, how it is distributed. If you go deeper, how it will be changing, all those things we will see later on. But the time being, when there is a soil and water only in a soil mass, because of self weight, what is the stress. So, consider a soil mass having a horizontal surface and with water table at surface level. So, that means you can take a something like this, the total vertical stress, that is the total normal stress on a horizontal plane. So, suppose the soil mass is extending here, and I will just draw a line here, and what is the total stress acting at this level I have to assess. So, for that what you have to do, this is the total, that means because of this soil above this level, how much pressure is giving at this level. So, that is the thing to be that is the thing is defined as sigma, total stress. At a depth z, suppose this depth is suppose z. So, at a depth z I have imagined a plane, and on that plane because of the self weight of the soil, whatever pressure is coming, that is actually total stress. So, and solid plus water per unit area above the. So, you know that because of this, if there is a water table also here or whatever may be. So, water table also suppose here, then the unit weight to be defined here as gamma saturated, and then it is actually if I take a soil column like this, sorry. If I consider a soil column as I have drawn before, and we have done this at a depth z, and this is water table also here. This zone gamma will be gamma sat, and I want to find out because of this what is the pressure at this, that is nothing but sigma. Now, while doing this, we have to do. So, if I consider a soil column of unit cross section area, this is a unit cross section and this is the soil column. If I do, then what is the weight of the soil column? This will be gamma into z into 1 into gamma z into 1, and since unit ratio, it will be gamma into z ultimately. So, total weight will be gamma into z only and divided by again cross sectional area 1. So, ultimately gamma z. So, it will be, so since this unit weight is saturated, so it will be gamma saturated into z. So, with increase of the z, the total stress also will be increasing. That means, if I draw, so it will be something like this. So, with the change of depth, your sigma v is increasing. Now, the pore water pressure again I can think of, suppose this is the one is there and this is water table is here, and because water pressure hydrostatic pressure, you know, it will be increasing with depth like this, and this will be how it will be, this will be gamma w times, suppose if it is z. So, gamma w is z. So, this is that u at any that same depth, if you want to calculate, that become gamma w times z, because this is all fluid mechanics and many places you do the hydrostatic pressure at any depth. And now, you have got by definition sigma dash will be equal to sigma minus u, and then you can see that it is become gamma sat, actually it is gamma sat into z minus gamma w into z. This is the thing we have. Now, if I take z out, then gamma sat minus gamma w, and this gamma sat minus gamma w, we use another different term, that is actually called gamma submerged, or sometimes it is called gamma buoyant, or sometimes use gamma sub symbol, sometimes gamma dash also use. So, that is the thing is given, gamma dash into z means gamma submerged unit weight, gamma submerged into z, and gamma submerged is what actually it is gamma saturated minus gamma w. So, this is the principle generally to be used for finding out the stress because of the self weight. Now, suppose this is a problem, a layer of saturated clay 4 meter thick is overlain by sand 5 meter depth. A layer of saturated clay 4 meter thick is overlain by sand 5 meter deep. The water table being 3 meter below the ground surface, the saturated unit weight of the clay and sand are 19 and 20 respectively above the water table. Above the water table, the unit weight of the sand is 17 kilonewton per meter cube, and if sand to a height of 1 meter above the water table is saturated with capillary water, how are the above stresses affected? So, this part I can discuss later on, but other part we can do, like there is a 5 meter sand, saturated clay 4 meter thick is overlain by sand 5 meter deep, and the water table being 3 meter below the ground, and so these are the things I will take. Suppose you have this is 5 meter sand and this is 4 meter clay and water table 3 meter below this. So, you have to find out, and this is unit weight is 17 and this one is 19 and 20. So, I have to go back. You can see the saturated unit weight of the clay and sand. Clay is 19 and sand is 20. Sand is 20. So, this will be 20 and this will be 19, and this is 3, this is 2 and this is 4. And then you have to find out the variation of stresses. What is the total stress, what is the pore water pressure, and what is the so generally we do this way. We can take 3 part for that sigma, and you can see up to this it is this is sand, this is also sand, and this is suppose clay, and then this is actually it will be 0 here, no depth soil. So, no weight. So, 0 into 0, so 0, and it will be increasing with depth actually 17 into z, it will be increasing. So, at this level, so 3 into 17 it will be 51, and then so at this level that much pressure already there. Then because of this layer again the further addition will be there. So, that will be gamma total, that means 20 plus, so that will be 51 plus 20 into z, if I consider z from here. So, if it is 2 meter, so 20 into 2 40. So, at this level, so it will become 91. So, this is 51, this is 91, and then again 4 into 19 plus 4 into 19. So, it will be 91 plus so 177 kilonewton per meter square, and then U we will be considering water table is here only. So, hydrostatic pressure will be 0 here, that means atmospheric, and then it will be increasing over depth, and it will become say gamma W is gamma W into Z. So, gamma W is the 9.81 into Z actually will be increasing. So, this will be 2 plus 4 6. So, 6 into 9.1 6, 58.86. So, this is sigma and this is U. Then I will get now effective stress. So, effective stress in above water table, since a dry unit weight is used, there will be no change. So, this portion will be remain unchanged, and when you go beyond below the water table, then your sigma dash will be equal to sigma minus u, and this sigma minus u, that means here this value will be there at this level 91, and at this level it is 9.81 into 2. So, that means 2 19.62, this is 19.62. So, this is 19.62. So, your 91 minus 19.62, this will be whatever value will be here. So, this value will be here, and similarly at this point you will have 177, this one will have 177 minus 58.86. So, whatever value it comes, that will become at this point. So, that means this is the procedure and to be followed, while sometime in many places that stress strain or the axis versus stress when you calculate, we do in this direction. Okay, stress is going this direction, and but we generally are not familiar with that type of thing. Always ground surface to be taken as 0, and when you are going downward, that will with the increased pressure. So, you will be doing this direction only, it is not in the reverse direction, it will be always in this direction, and it will be shown diagram, sigma diagram, U diagram and a sigma dash diagram. So, these 3 diagrams should be side by side, so that I will get this and then get this. Once you get this and this, then this minus this become this. So, that is the way one has to complete. So, this is the way actually, and the entire diagram is drawn like this, but here actually sometime instead of using in civil engineering particularly G value or 9.81 or gamma W as 9.81, many times actually civil engineering application using gamma W 10 also can be used, but since in the most of the competitive exam etc., we do not know what value they expect. So, better to use the correct value of 9.81 and then that is better. So, if you use 10, actually this type of value will get whatever I have got before, and you will get this one actually. So, better to use 9.81 for gamma W, and I have used also in my calculation. Now, actually variation in effective stress with the shift in groundwater table, actually that is what I have mentioned, that the effective stress will change with the variation of different things, like water table is one of the most significant parameter. With the variation of that, your effective stress can change, and you can see for water table below the ground surface, and when suppose this is the ground and water table is somewhere here, a rise in the water table causes decrease in effective stress. So, if water table from here it goes up, then at any depth below the this level, your effective stress will be decreased. That application I will show later on. So, that is why this should be remembered as a rule almost. A rise in water table causes decrease in effective stress, and a fall in water table produces an increase in effective. Suppose water table is here, and then water table goes down this direction, then at the same point you will see increase in effective stress. So, because of that, many situation, many excavation time, if the high water table is there, and then we have to lower the water table because to make the soil stronger. So, that application I will show later on. And for water table above the ground surface, a fluctuation in the exposed water level does not alter the effective stress. That means what? If the water table is somewhere here already, now water table if goes 2 meter or 5 meter or 10 meter or again come back, and if I consider at this point, because of this change is water table, what generally effective stress will not change, because that calculation also I will show you later on. So, that means if the above groundwater level, if there is any change in groundwater table, it will not make any change in effective stress in the soil below the ground level. And the effect of a shift of in the ground surface will cause change in effective stress. Suppose ground was here today, and because of deposition ground mark is here. So, at this point definitely effective stress will increase, and suppose ground mark was here, because of erosion it has decayed. So, it came down here, it was gone up and it gone down, then at this point same point, if because of the erosion if it comes down, then effective stress will decrease. That is what the ground surface will cause a change in the effective stress of magnitude equal to the change in the overburden pressure. So, if this is the layer, if this much overburden you have to calculate. So, because of that overburden, what is the pressure, that much will change. So, that is the thing you have to remember. So, these 3 points, that means water table change, when water table from the inside the ground goes up, then effective stress decrease, water table goes down from the original ground level, it effective increase, and above ground level, if water table any change does not make any change in effective stress, and of course, change in ground level itself will cause the change in effective stress. So, that how it will be, that is actually if it is overburden added, that equal to overburden, and if the overburden decrease, then minus overburden pressure. So, that is the thing shown here. With this I just effective stress just complete. Thank you.